Hi, I'm Sagnik Bhattacharya, and this is my submission for gold points in Project Zero for CS61B Spring 2019. I have implemented elastic collisions in my n-body simulator because, well, what kind of an n-body simulator would be complete without collisions? In order to implement collisions, I use simple physics equations for elastic collisions in 2 dimensions. So it's just like the same 1D collision equations, but applied separately to both dimensions. And in the code, I basically, after computing the final positions due to gravitational interactions, my code then checks for collisions, and it also then adjusts the velocities of objects using the information about their masses and their current velocities. If they're colliding. If they're not colliding, then you only see the effect of gravitation. And I would like to mention that I briefly considered using things like quad trees and bounding volume hierarchies in order to speed up my algorithm to do better than order of n squared. But since the gravitational interactions are going to be order of n squared anyway, I did not bother using any speedups for the collision detection because it wouldn't matter anyway. My simulator would still be order of n squared. So that was enough talk. Now let's look at some demos. So we will begin with the most basic demo. This was just a sanity check because I just wanted to make sure that I don't have like any subtle bugs in my collision detection. So in this demo, well, it went by pretty quickly. Let's do that a little more slowly this time. So over here you can see that Earth is colliding with Mars. Oh yeah, and you can see this is not colliding because I was using the wrong simulator. Now, watch them collide. There you go. Earth collides with Mars, and Mars is just slightly lighter than Earth, and so you can see that Mars sort of speeds away from the Earth after they collide, which is what you would expect to happen if you work out the physics equations. Now let's look at a more interesting demo with more objects. And here you can see there are lots of Earth's weight. This is too slow. I need to speed it up. And here we go. Now you can see these are about to collide. And there we go. Collision. No collision. Wrong simulator. That's why. Now you know that my simulator actually works. And now things are going to collide. They will. Just wait for it. Wait for it. Wait for it. And there we have collisions. And something you might notice is in a couple of places like over here and here, you can see that a bunch of these Earth objects are sort of clustered together. Like they're sort of sticking to each other. And this first, when I initially looked at this, I was like, wait, is there something wrong with my algorithm? But then I realized that no, there's nothing wrong with my algorithm, because objects like the Earth are really, massive, so they have like a really strong gravitational pull. So if two objects with similar masses collide and there's a strong attractive force between them, but their velocities were not too high, then what happens essentially is they stick together, because even though they collided and that sort of pushed them away from each other, in the end what happened was, since they're so close, the gravitational pull was just way stronger, and that just causes them to clump together. And this clumping behavior is especially evident in this last demo called SPH3. And here you can see there are lots of bodies with similar masses, and they form a bunch of these clusters, like these clumps of a couple bodies. And essentially, this is how planets form, when objects with similar masses moving at relatively slow speeds compared to their masses start, colliding with each other. They tend to stick to each other, and they usually coalesce into bigger bodies. And so you sort of get to see this sort of, planet formation physics as well in the simulator. So I thought that was really interesting, and that's it for my submission.